So in previous classes, we've talked about concurrency, and I've made the point that this class is largely about concurrency. But it's also important to know at least a little bit about alternative ways of taking advantage of multiple cores, and that's what we call parallel programming. So what I'm going to talk about here is parallel programming and the key parallel programming concepts. I'll show you some examples of how to do parallel programming in Java, but the bulk of the parallel programming material was either covered in a previous class that you guys took last semester or will be covered in the same offering of the class in the fall. And I'll also talk about when to apply parallelism. So parallelism is a form of computing that performs several steps on multiple processors or processor cores. Nowadays, it's really multiple processor cores. Back in the old days, it was multiple processors where every processor had one core. Nowadays, it's typically a processor with multiple cores, but sort of the same idea. So there are three primary steps or phases. Step one is the splitting step or the splitting phase, which takes a big task and partitions it or splits it up into a bunch of subtasks. And ideally, these tasks are split evenly and they're split efficiently. So if it all goes well, we really like to split these things in half. And the reason why we want to split things in half, wherever possible, is you end up with a very nice balanced tree of splits, which is never more than log n deep if you always split everything in half. Once you've split everything up into an appropriate number of smaller subtasks that are, let's say for sake of argument, atomic in their remaining subtask size, what we're then going to do is we're going to take each of these subtasks and we're going to run them in parallel. Now what's interesting about this is that each subtask is running sequentially with respect to itself, but the combination of all those subtasks are all running in parallel. So each subtask is doing its own thing sequentially, but all the subtasks are running together in parallel. So if you kind of look at this, you got the subtasks, then you're going to take each subtask, you're going to process each of those things sequentially, but the whole kit and caboodle will run in parallel. And then the third step, or the third phase, is to take the sub-results from all the subtasks that were all running in parallel and merge them or combine them back together again into a final reduced result. So this split, apply, combine paradigm is really at the essence of parallel computing. Now, the whole purpose of this, and we'll talk a lot more about this in the other course, but in a kind of a Cliff Notes summary here, if you can't efficiently partition the tasks up into subtasks and efficiently combine them, parallelism may or may not actually give you a win. You may be doing a lot of extra work for no particular improvement. But if it all goes well, you can view parallelism as basically an optimization designed to improve performance. And the way to think about the performance dimensions we're trying to improve are throughput, scalability, and latency. So throughput obviously is about how much work you can do per unit time. Scalability is about how many things you can run in parallel. And latency is how quick the response time is to do any particular task. The next question is, when should you apply parallelism? Just because you can do it doesn't always mean you should do it. So what are the circumstances under which it makes sense to use it? So parallelism works best under certain conditions and certain assumptions. Assumption number one, if tasks are truly independent of each other. This is often something referred to as embarrassingly parallel. It's a really funny phrase. People say, embarrassingly parallel, what does that mean? It basically means that there are no dependencies between the separate tasks. And it's embarrassing because as the number of cores increase, you can simply keep running all these tasks in parallel and you'll get more and more results. The analogy to literature is embarrassment of riches. So if someone is ridiculously wealthy, like Bill Gates or whatever, it's called an embarrassment of riches. Now, he's probably not actually embarrassed about being a gazillionaire, but you get the point. So embarrassingly parallel simply means there's little or no dependencies or need for communication or interaction between the tasks, and there's no need to share results between them as they're being computed. As they're being joined back together again, then we're going to merge them back. But as they run independently, they're embarrassingly parallel because they're independent. Parallelism also works best if there's lots of data and lots of processing to perform. So the more data, the better you're going to be able to take advantage of multiple cores. The the more processing, the better you're going to be able to take advantage of multiple cores. And in fact, there's an equation visualized through this little chart that shows the ideal circumstance for parallel computing. And the two dimensions on the x-axis is n, and the y-axis is q. N stands for, as almost always in computing, the number of data elements to process. So that's n, right? If you think about log n, or O of n, that means n is the number of something. So if you have lots of things to process, then you're better off running these in parallel. And Q is kind of a weird thing. It really quantifies how CPU intensive the processing is. So if you have lots of data and each data element takes a long time to process, then you get more advantages of parallelism, especially when the tasks are independent. If you only have a small number of data elements, if you only do a little bit of processing per data element, it's usually easier just to do it sequentially, or faster to do it sequentially, and easier typically too. Another condition under which parallelism works well is when the threads that are doing the computations in parallel neither block on I/O or synchronizers or whatever, nor share mutable state. Mutable state being that state that gets changed by multiple threads. We talked about that a bit earlier when we talked about concurrent processing. So if threads don't block, if they're CPU bound, or they are not sharing state, they're independent of each other, then parallelism works a lot better. And we'll see that there's this focus in Java on the concept of fork join and the fork join framework, which we'll cover a little bit in this class, but it's really more of a parallelism concept, and work stealing, which is another topic we won't cover as much as I'd like to in this class, but we'll cover it in the other one. If you want a preview of fork join and work stealing, you can take a look at these Wikipedia links. And of course, the more processors, the more cores, the more physical hardware elements there are that can run in parallel, then it's going to work better. If you only have one core, there's really not a whole lot of benefit of parallel computing. Okay, so that's just a quick overview of parallel programming, and we will come back in a moment and talk about the frameworks in Java to support that.